Welcome to this explainer. Today, we're diving into a real cinematic, scientific mystery about the invisible forces that literally protect our world. We're going to journey from the very edge of space all the way down to the molten center of our planet, just to understand this incredible phenomenon that actually makes life on Earth possible.
So Earth has an invisible shield protecting us from space. But here's the catch. This shield is constantly changing. Why is that? We basically live inside this massive magnetic bubble, and its shifting, highly unpredictable nature is honestly one of the most fascinating puzzles in all of Earth science.
That shield is what we call the magnetosphere, and it acts as our planetary gatekeeper. You see, the sun is just continuously spewing out this intense stream of charged particles known as the solar wind, right? Alongside all these cosmic rays from deep space. And without our magnetic field, our atmosphere would eventually just get totally eroded away by all that harsh energy. But instead, the magnetosphere repels this harmful radiation, trapping most of it at a really safe distance in two massive, donut-shaped zones called the Van Allen belts. But to actually understand why this shield up in space changes, we've got to look downward. We need to literally peel back the layers of the Earth. Now, we're all pretty familiar with the solid crust we walk on every day, and maybe the thick, kind of caramel-like mantle right below it. But if you travel about 3,000 kilometers underground, you hit the core. And the absolutely crucial distinction here is between the solid iron and nickel inner core and the liquid outer core. That viscous liquid layer, that is the hidden engine of our magnetic field. Okay, so how exactly does an ocean of liquid metal create a magnetic field? It's through a mechanism called the geodynamo. Think of it a bit like boiling water on a stove, but combined with the spinning of a bicycle dynamo. Convective forces are just constantly churning these superheated molten metals, and the Earth's rotation swirls them into these massive whirlpools. This completely roiling, rotating liquid metal generates electrical currents that are hundreds of miles wide, and it's that massive electrical current that generates our continuously changing electromagnetic field. Now, because this liquid engine is constantly churning and shifting around, the magnetic field it creates is also in constant flux, and this leads to one of the absolute biggest misconceptions out there when it comes to navigation: geographic north versus magnetic north. Your geographic north pole is totally fixed. It's the absolute permanent axis of Earth's rotation. But the magnetic North Pole, that's simply the wandering location on the surface where the Earth's magnetic field points vertically downward. And because the liquid iron deep inside the Earth is moving, well, the magnetic pole just wanders right along with it. And this constant movement creates something navigators have wrestled with for literally centuries: magnetic declination. Basically, this is the shifting angle between the direction your compass points, magnetic north, and true geographic north. If you're out hiking in the wilderness or sailing across the ocean, you have to constantly account for the shifting angle. Why? Because the magnetic field lines aren't just these perfectly straight, neat paths connecting the poles. They warp, they stretch, and they bend based entirely on what's happening deep underground. So just how fast is this magnetic pole actually moving? Well, let me give you a number to put this in perspective: 34. For a really long time, the magnetic North Pole drifted at a pretty leisurely pace of less than 10 miles per year. But since the 1970s, that drift has accelerated dramatically to over 34 miles per year. Scientists are tracking it incredibly closely right now, as it practically sprints across the Arctic.
Now, all this internal shifting also creates regional anomalies, like the South Atlantic Anomaly. This is a regional weak spot in the magnetic field located right over South America and the Southern Atlantic Ocean. But here is the crucial takeaway: it does not affect life on Earth. Now, it's true that this dip in the magnetic field allows solar wind to get a bit closer to the surface, which can occasionally fry the electronics on passing satellites, but it poses absolutely zero danger to humans on the ground. It's really just a fascinating localized quirk of the geodynamo.
At this point, you might be wondering, how do we actually know so much about the deep history of these changes if we've only had compasses for a few hundred years? Enter paleomagnetism. This is the study of Earth's past magnetic fields, beautifully recorded in ancient volcanic rocks and sediments. See, when lava erupts from mid-ocean ridges, it obviously cools and hardens. And as it drops below about 1,300 degrees Fahrenheit, the iron-rich minerals inside that lava align with the current magnetic field, permanently freezing its strength and direction into the rock. It's literally like a fossilized compass needle. By studying those incredible rocks, scientists have gathered data stretching back 160 million years from mid-ocean ridges, and they've discovered something absolutely wild. The poles have completely swapped locations hundreds of times over millions of years. The last magnetic pole reversal was about 780,000 years ago, and the average interval between them is around 300,000 years. Just compare that vast, mind-boggling geologic history to the mere 200 years we've actually been taking direct observations.
Okay, let's pause here. Because whenever people hear about the pole swapping, the rumors and pseudoscience just start flying across the internet. So let's be absolutely 100% clear. Geomagnetic reversals take hundreds to thousands of years to happen, and they are not imminent. The field does not just switch overnight, and it definitely does not disappear completely during a reversal. Sure, the magnetic field gets jumbled. It weakens a bit, and multiple poles might temporarily pop up at unusual latitudes, but the magnetosphere is still there, still protecting us. A pole flip is this incredibly slow, irregular process, and despite what you might read online, one is absolutely not about to happen.
To really keep everything straight in our heads, we have to draw a hard line between internal changes and external disruptions. On one hand, we've got the permanent, slow changes generated deep inside the Earth's outer core by the geodynamo, things like the moving poles, anomalies, and those reversals we just talked about that unfold over years to literally millions of years. On the other hand, we have the temporary, highly rapid disruptions caused externally by the sun's space weather, which act over just a matter of days or even hours. Let's talk about those external disruptions for a moment. Extreme space weather, like massive solar storms, can cause temporary cracks in our shield. When the sun violently buffets our magnetosphere, it creates geomagnetic storms. The positive result of this? Absolutely spectacular auroras, the northern and southern lights, as those charged particles rain down into the upper atmosphere. The downside, though, these intense, temporary distortions can pose very real risks to our modern power grids, our satellites, and our global navigation systems.
So how exactly are we piecing this giant puzzle together today? Well, scientists use a seriously impressive array of technologies to decode the mystery. We use ground-based magnetic observatories, historical navigation measurements, and those paleomagnetic rock records we discussed. But we also have incredible modern tech, like the European Space Agency's Swarm satellite constellation, which precisely measures the field from space to help us understand what's happening deep inside the planet. Scientists then take all of this data and feed it into supercomputer geomagnetic models.
But despite all this amazing cutting-edge technology, we still arrive at the big mystery. What exactly triggers magnetic reversals and drives the geodynamo? We know the basics of how it works, sure, but the precise fluid dynamics of that liquid iron outer core, the exact schedule of reversals, and why the field changes in such endlessly complex ways, those remain profound, unanswered scientific mysteries. Our models are incredible, but the center of our planet is still vastly uncharted territory. Which brings us to our final thought today. Deep beneath our feet, liquid iron is constantly moving, changing the invisible shield that protects our planet. But what controls this enormous engine, and what will Earth's magnetic field look like thousands of years from now? The Earth is alive, both on the surface and deep within, and its magnetic personality will keep scientists guessing and searching for answers for generations to come. Thank you so much for joining me on this explainer, and I hope this leaves you wanting to learn even more about the incredible, invisible forces shaping our world.